this video, we're just going to cover the basic properties of alkanes. Properties of alkanes. And the first thing I want to teach you guys before we get into the sort of difference in boiling points, etc., is electro negativity. EN for short, as I'm going to refer to in this video. And I'm not going to explain electronegativity too much. I just want to state it as a point that if two elements that are bonded together have an electronegativity difference of less than 0.5, then that bond will not be polar. So if we look at these two bonds here, we know that carbon-carbon, I mean, they have the same electronegativity, so this one is going to be non-polar. And hydrogen and carbon, I think one's 2.6, one's 2.2. They don't have an electronegativity difference of greater than 0.5, so this bond here is also non-polar. This means that these alkanes can actually form instantaneous dipoles which actually induce neighboring dipoles. And what dipoles really mean is just sometimes the electrons in a bond here can sometimes shift too far one side, causing a disbalance in charge. Now these dipoles, let me draw just two CH4 molecules here, CH4 here, and we're labeling this as the sort of induced dipole-dipole interaction. This is what it's called, or as you may know it as a London force. And here you can see there's a weak London force. London forces are the weakest force, intermolecular force. However, we could compare it to propane. Propane here. CH3, CH2, CH3, CH2, CH3. And you can see here there's even though the induced dipole-dipole interactions here, the London forces here, are still weak, there's a much greater force here than between these two CH4s. So, I mean, you can obviously see now that the trend in increasing carbons will result in increasing boiling point. So you can see here the boiling point is quite low because the intermolecular forces are quite weak. However, this is going to be higher, relatively higher than methane. And I don't know the exact values here, but obviously you can surmise this. Funny enough, I do know that hexane has 69-degree boiling point. Who'd have thought I'd remember that, right? And I mean, obviously, we draw CH4. We draw butane. CH3. These are two butane molecules, and I'm showing you the instantaneous dipole interactions, induced dipole interactions. These are London forces, right? London forces, instantaneous, induced dipole forces, same thing. You can see there are more here, so the forces are even stronger here. And because of the higher surface contact areas, this causes more induced dipole interactions, which means more energy is required to break these. More, or you can reference here, causes more or stronger induced dipole-dipole interactions, which means more energy is required to break these intermolecular forces. And say you're faced with a 3-mark question here, and you're maybe asked, why does propane have a higher boiling point than butane? This is why. Now there's one more concept I want to go over very quickly, and that's the effect of boiling point on branches. So I'm going to draw butane here, and I'm going to draw an isomer of butane, methylpropane. Now, butane here is going to have the higher boiling point because of the same reason. Now, you can see overall there are more surface area contact points here, and what that means is there's technically a larger surface area here. If you think about it, it's more spread out, so there's going to be more surface contact points, which means more London forces, which means more energy. Sorry, we'll write stronger. And here there's less surface contact points, which means it essentially forms weaker. Each force has the same strength, but there's more induced dipole-dipole interactions happening, so in a sense it is a stronger force, which means it requires less energy. And because it requires less energy, it's going to have a lower boiling point. So sorry for the rushed video here, but hopefully this will make sense.